Talk is born out of a need that I have to combine my science tools and deliver some of that science over the internet, and ties, I think, really nicely into the theme of our keynote that we had this morning, and some of the speakers that preceded me as well, in showing all of the different things that have to come together to get science done with the tools that are out there. So I want to try and address what I mean by concurrent here. We all know that Python is adaptable and it's widely used in scientific computing and web development, and it's good for systems programming. And we might think at the outset that these three problem domains don't share a particularly large amount of things in common. However, I can actually detail with the project that I'll talk about today that they do in fact share quite a bit in common. There's some unique constraints. Unlike folks whose job it is to write code full time, I have many other responsibilities, so I don't get to rebuild my whole stack from scratch. I don't have time to develop an elegant solution, and I think that's common to a lot of the things that we see around as scientists. We pick up pieces that others have written and we glue them together. So it's very much a hacking kind of thing. With other duties I have, coding is rare and precious time, and if I'm going to be spending time coding, it really hurts to mode switch. And so there's different ways that have developed, I think, in Python of thinking idiomatically about doing systems programming tasks, and being a web developer, and being a data analyst. And that hurts, and having to undergo that mental switch is a productivity loss. And so you can see what I'm trying to build towards here is an understanding of, I want to try and illustrate what it's like to try and exist across all of these worlds and think in a consistent way about Python in all of those areas. And so I argue that a shared sense among disciplinary communities of the essence of how one deploys Python in the whole ecosystem sense for any problem is beneficial for the continuation and growth of Python's status as a go-to language for constrained practitioners whose job isn't computing or Python full-time. It's just it's a hammer that we pull out when we need to bash our data into shape. So we're all familiar with the magical feeling of encountering Python for the first time, and it makes us think that we can, with 4 lines, accomplish all our work, right? So we're gonna import our data, and we're going to import our science, and we're gonna import the internet, and in 1 line we'll call all of those things, and we're done, right? So the questions here are things like, how do I get to the point of importing? What sits on the back end of my code when I run it? Can those runtimes coexist? And especially, how will I know that those runtimes can coexist and that I'm not going to spend 2 or 3 days trying to determine whether or not this solution is going to work? We've got a lot of smart people in the Python community, right? We've got web people, and they develop things like Django and Tornado, pip, virtual env. You'll see them using that almost exclusively for their packaging and deployments. I have actually seen IPython, and I think IPython is one of these interesting things that sits at the junction of these 2 worlds. It's a terrific tool. And there's the PyPy project, which is very much a sort of prominent research activity at the moment. We've got science people with our tools, which are NumPy and SciPy. We like things like EPD that package up all of those difficult to compile things. We definitely love IPython. The notebook, which I also had my first experience with this week, was sort of a mind-blowing experience. And we have things like Cython and Numba that allow us to do sort of compiled code that is optimized in some way, and in some ways at a very superficial level you might think that PyPy and those things would share a similar goal. And so I list here, we have packages. How do we do the packaging? What's the run environment? And what are the optimization tools we use to accomplish the work? So what constitutes best practices in all these areas? And I'll quote import this. Our goal is one obvious way to do it, and I'm talking about the whole ecosystem and not just at a language level here. A quote here from David Beasley, who's posted on Twitter back on July 12th, this terrific quote, very, very elegant, about the wild fortress of scientific computing is littered with the silver bullet-ridden corpses of compilers, languages, and tools, and computer scientists would be well advised to listen carefully if they want the keys to the city. So I think that's very, very wise and timely advice. So while I agree, I want to maybe toss out a suggestion for an addendum to that perhaps if we're looking to bridge these worlds and work in both of these worlds, it would be good to act as a tour guide to our science, and just sort of hurling our menagerie of experience over the wall at curious onlookers would certainly convey what it's like on the inside, but might not be the most effective way. And so, this cross-cultural communication is hard, and it takes some work. So here's my story of what I do. I'm a meteorologist by training, but I play with electrical things, and so that makes me a bit of an odd duck. The sensor you see on the right-hand side here is a station that's part of the West Texas Lightning Mapping Array. This is a system that listens with that antenna on top for VHF spherics. Think the noise you hear on AM radio when a lightning flash happens. Every time a lightning channel steps, every little kink in a lightning channel has an opportunity to produce one of these radio pulses. And so we have 10 stations. They're located over the area of about a county, about a 50-kilometer diameter area. Each station records the peak VHF pulse every 80 microseconds to a timing precision of on the order of nanoseconds using a GPS signal. And then there's a real-time UDP stream. There's actually a little Unix box at every one of these stations. UDP stream of peak pulses is streamed out of the stations over the internet every 400 microseconds. So that UDP feeds some code that triangulates those sources into a location back in space and time, and then from those sources we do some derived products and deliver those products over the open internet. And we cover a relatively wide area with one of these systems. We can see lightning flashes basically over all of West Texas with a network that's easily reachable, the whole network by car in one day. So what do the data look like? This is not the lightning data that you see on the television. This is 5 seconds worth of data from basically a single enormous flash. It produced an ionospheric electrical discharge that was photographed from New Mexico. This flash occurred over the Texas Panhandle. And you can see that in about 5 seconds we've detected 4,000 points. And the plot here, which I'm going to show you an interactive version in just a second, has a time height on the top, so that's time that moves from left to right. Color indicates the evolution of time, so the blue points are early, red points are late. The big square on the bottom is a plan view, and that's over about 150 by 150 kilometer area, so it's one flash covering with a connected electrical tree that whole distance. And then if you fold up the panels above and to the right of that, you have east-west versus height and height versus north-south, and so it's a way of viewing the four-dimensional character of the data in a single plot. And so these are the kinds of points that are delivered in real time every second and are part of this real-time processing stream. Let me jump over here to a Matplotlib window that is an interactive data browser I wrote, so I can animate this for you here, and we can watch the flash develop. All right, and what I want to get to here is 37.6 to 38.8 seconds. And I'll show you a little bit of a zoom in on just sort of the early portion of this flash. So you can see it has all this activity associated with the core of the thunderstorm. It's relatively compact, maybe 10 kilometers in extent, and then you get this channel that moves out into an area of light, steady rain and branches out and discharges this whole region all at once, and it's that big discharge that is what triggers the sprite then in the upper atmosphere. Once we've detected all of those points, we grid up we cluster those individual sources into flashes using space and time criteria. And I'm interested in exploring some of the scikits.learn to see if there's some algorithms we can make use of there, actually. And once we've got those flashes, we count up those flashes on a grid and produce plots like you see here. Lower left is the average flash area at a pixel, and the upper right is basically the number of flashes on a log scale. And then these are delivered to the National Weather Service in real time every minute once we've aggregated enough flashes together to make a meaningful plot. What does this look like on the back end? So here's the big flow chart. We have our lightning mapping array field sites in the upper left corner of the plot there. Each of those streams UDP on a separate port into our central processing server. There's a little Python script that aggregates those together, so there's a systems programming task. And then that's restreamed on localhost back out to a single UDP port into that block box compiled code that locates our sources. All the red boxes you see on this plot are Python. The black boxes that I have absolutely no control over and probably never will are in light blue. And then the top half of the diagram is the real-time stream every second. We stream those sources that are located into a tornado instance that restreams those points back out over a WebSocket and therefore makes this stream available on the public internet. There's a Java client that some colleagues wrote that then picks up that WebSocket stream on a local client box anywhere in the world and streams with 1 to 2 second latency these detections of lightning flashes. So I've been at home, seen it flash outside, seen something display on my screen, and then heard thunder. It's that kind of thing. Terrific fun. So there's a little Python script that it's pure Python, so I just send that out to anyone who wants to read the data, and it reads the WebSocket and streams back to UDP on localhost. The difficult part of the stack, that top half was pretty trivial in the end. The lower half is the part where I'm trying to do my science stuff, and that's a lot more complicated. The located sources are saved to an ASCII point file that's made by some other person's code. It's an amalgam of shell script and Python and some Java and some compiled C to make a web archive that's served over traditional Apache. Love to replace that with matplotlib. And there's another stream that actually does the gridding. We take those ASCII point data and they go into a Python driver where I stream those points out to Fortran over standard out. I gather back the flashes that the Fortran spits out. That's again someone else's code. And then those flashes and points are saved out with PyTables to an HDF5 file. And then that HDF5 file is read back in. Products are gridded up, saved out to netcdf. The gridding actually uses David Beasley's coroutine method to do that, and that source code is available on Bitbucket under LMA tools if you want to take a look at how that's done. And then those netcdf products are put on an LDM server, which is a real-time data distribution server that's common in meteorology. And then that gets sent out to the weather service along with those ASCII point files. So a lot of moving parts, and Python's insinuated itself into every corner there. But it's complicated and kind of brittle, and the parts don't always play well together. So I'm using pip and virtualenv to do my deployment on the back end, and my experience was that generally I can't use pip as elegantly as the web guys get to because of all of the compiling that has to happen, and it's a lot more fraught than calling setup.py from something from the package index. Again, there were troubles with using the science tool stack, using EPD with virtualenvs, and I had to go find some blog posts to do some path hacking, and it's just a little fiddly. I've got Python streaming standard out to Fortran, which is called by cron, and debugging that is not in any way fun. Again, I think the web guys, have tools to do this stuff, and maybe introspect a little better, and there's best practices in that community, and how can we get access to some of those as scientists? And overall, my experience was that I had an easier time figuring out systems and web type deployments for Python than I did in getting my science code to run as a scientist. So this is my plea or flag for, do we need to think about the ecosystem as a whole? And so you might say, maybe I need to learn a few things about compilers and legacy code, rewrite some of my stuff in Python for clarity, tackle with some optimizing hints, take some time to understand packaging. And I agree with those things. I really would like to. I've written more code this week than I have in the past couple years probably. And so there's real scheduling pressures, and I'm looking, because I also like the rest of my job, I have to cut myself off at some point. So is there a way that we can smooth some of these friction points? So we're back to the beginning now, and the big picture concerns. There's good work going on in the web and systems and science communities with some overlapping concerns. We have packaging and optimization and compiler work. And so where do I spend my time learning if I want to work in both of these problem domains? Which things are going to be long-term stable solutions? How will I know? Every time I go to a conference, or I look at conferences that are reported out on Twitter, you hear about some new optimization or concurrency solution. And so how do we identify that things are stable? EPD is very comforting in that way, because I know I can count on all of these things being bundled together in a workable fashion. So this is my summary here of the mechanics of using packaging and compiler infrastructure, made worse by data I/O and flow through a mixed stack, is by far my biggest thorn, and that's, I guess I'm concerned a bit as I see the proliferation of different customized compiling methodologies. Is that kind of conflict only going to proliferate? And the time will tell, but I think the web and science are only likely to become more intertwined, and I think you saw some just terrific examples of that with our keynote this morning, of a really good example of why that's beneficial to do so. And so right now we have specialists working well in their own problem domains and doing great stuff. And so what could we do if, with real-time data delivery and archive and query and community-driven data mining and visualization and technique development, if we had the best ideas from both domains to really smooth the path for normal guys like me? And I don't think we have a quick answer to that solution, and it's it's more of an orientation in our souls. How do we care about these things going forward, and are we paying attention to these things as we're making decisions about how we develop our frameworks? No question that Python it has the right people and ideas, and really the right field to the language to make this kind of thing possible. And so I'm excited to see where things go, and I'll leave you with the fact I'm teaching the next generation how to be computational scientists who live in the internet age. So what are the best practices that I should teach them, and look forward to coming to future meetings and learning more good things that I can pass along as the years go by. So, thanks.
So I have the same sorts of problems with building this big stack to solve complicated scientific problems. And we've been trying to get some people together and some ideas on how to improve this. And I think part of the problem is that doing something as complicated as what you're doing, you're not just in Python, right? And getting that whole stack to work together is really, this time it's unique. Well, it's not unique, but this is a problem that high performance computing, computational science has to deal with. And what we found is that there's not any support from sort of the mainline Python world for solving this, because they can operate within Python and be happy. And even to some extent, I think things like EPD, there's really not enough overlap with these things with InThought's business model to really move that ahead through something like InThought. And so I'll mention this, that we're working on it. There was a blog that was kind of running on it for a little while, but that's kind of gone away as we've kind of picked some guys to work on it or trying to move forward. But it doesn't have a name. I've got a version called Python HPCMP that's sitting on GitHub that I think is actually open, but it's really just a hack of what previously existed. But I think if there are other people in the room, and certainly you would be interested, it'd be great maybe if we could talk about that afterward. A lot of people at supercomputing this year at our Python HPC workshop were really interested in this as well. So it seems like a big problem, but it doesn't, from what I can tell, seem like it's going to get solved by the main community. Yeah, right. Yeah, and I'm wondering if there's a way to do some engagement with the main community, because you occasionally see interested parties that think what we do is interesting, and so what's their hook to get involved? There's some YouTube videos of Guido and other fairly well-known people more or less saying it's our problem. So that I think it has been raised, this issue, and the importance of it has been raised multiple times, and it's not like they've just kind of said go to hell. It's more of, that it's our job, I think. Yeah. So.
I have a question. You said at the end that you're thinking what are the best practices to teach to scientists. Mm-hmm. Are you aware of the software carpentry project? I am, and I've recommended that to several students, that they go through that as a foundational exercise, and those basic tools of version control and how do you think about programming with an array and all of those core ideas, absolutely. And that's foundational in homework assignments and things that I do. I try and build that in. So that software carpentry is a terrific tool. Okay. All right.
So we have any